In this video, I'll be going through the 2022 Scholarship Physics paper. Question 1. The description of the photoelectric effect and the Bohr model of the atom both involve the concept of quantization of energy. There are similarities and differences in how this concept is applied in these contexts. Describe one difference in the use of the concept of quantization of energy between the photoelectric effect and the Bohr model of the atom. The photoelectric effect involves the quantization of light to explain particle-like behavior. That is, that there were several observations which didn't make sense using a wave model of light. It only makes sense when you consider light as quantized particle-like packets of waves. The Bohr model involves the quantization of electron energies within the atom. A laser typically consists of a medium that emits light placed between two mirrors that form a cavity, as illustrated on the right. The cavity is similar to a closed box for the emitted light waves. The light-emitting medium can emit a continuous spectrum of light within a narrow range of wavelengths. The minimum wavelength of emitted light is 480 nanometers, or 4.80 times 10 to the minus 7 meters, and the maximum wavelength is 490 nanometers, or 4.90 times 10 to the minus 7 meters. The cavity is 5 centimeters long, or 0.05 meters. Some wavelengths within this range are able to form standing waves within the cavity. These are called standing wave modes. Calculate the total number of standing wave modes possible in the cavity within the emitted 480 to 490 nanometer range. You might recall for standing wave patterns where we have a node or antinode at both ends, we can write lambda equals 2L over n. Rearranging this for n, what we can now do is substitute our minimum and maximum wavelength and determine its corresponding mode. Our minimum harmonic is given by our n equation, where our L is 0.05 and is going to occur at our longer wavelength, 4.9 times 10 to the minus 7, which gives me 204,081.6, which, because our harmonic can only be a whole number and we don't quite get down to 204,081, our minimum harmonic must be 204,082. Our maximum harmonic can be found the same way, but this time using our minimum wavelength, which gives me 208,333.3, which means our highest whole harmonic is 208,333, which means our amount of modes is our maximum minus our minimum, which gives me 4251. The process of nuclear fusion in the Sun releases energy which spreads through space in the form of electromagnetic radiation. The photons that make up this radiation carry momentum as well as energy, with the momentum per photon given by P equals h over lambda, where h is Planck's constant and lambda is the photon wavelength. The Sun loses 4.30 times 10 to the 9 kilograms of mass each second due to nuclear reactions. Estimate the force exerted on the Earth by the photons it receives from the Sun. Assume each photon has a wavelength of 550 nanometers, or 5.5 times 10 to the minus 7 meters, and that every photon that reaches Earth is absorbed. This is going to involve a number of steps. We can find the number of photons per second by considering that our energy per second is going to equal our mass per second multiplied by c squared, and is going to equal the number of photons per second multiplied by their individual energy, which we can write as hf. And now for convenience, because we're given the wavelength but not the frequency, we know that c equals f lambda. Rearranging for frequency, making that substitution, where we can simplify this by dividing both sides by c. And now solve for n. Put our numbers in, which gives me 1.07 times 10 to the 45 per second. What we now need is the momentum of each photon. We know that the momentum is h over lambda, and we know both, which gives me 1.21 times 10 to the minus 27 kg meter per second. We now need to find the proportion of these photons impacting the Earth. If we imagine a sphere around the Sun with the radius of Earth's orbit, where the proportion of the photons hitting the Earth is going to be the cross-sectional area of the Earth divided by the area of the sphere with a radius of the Earth-Sun orbit. The cross-sectional area of the Earth is pi r squared, where our r is the radius of the Earth, which we're given all the way up here as 6.37 times 10 to the 6. The area of the sphere at Earth's orbit is given by our equation here, 4 pi r squared, where our r is the mean Earth-Sun distance, which gives me 4.51 times 10 to the minus 10. Now, the force experienced by the Earth can be written as the change in momentum divided by the duration over which it changed. For a duration of 1 second, the change in momentum is going to be the number of photons multiplied by the momentum of each photon multiplied by the proportion of them impacting the Earth, which gives me 5.84 times 10 to the 8 newtons. Comment on the significance of the size of the force exerted on the Earth by the photons. Now, the force might sound very large, but we need to relate this to the mass. We of course know that force is equal to mass times acceleration, and so we know that the acceleration is going to equal force divided by mass, where our force is what we just found, and our mass is the mass of the Earth, 5.98 times 10 to the 24 kilograms. Which gives me 9.76 times 10 to the minus 17 meters per second, which is negligible. If the Earth were covered by ice, it would be more reflective. Explain how this would affect your answer to part C. If we imagine the Earth, if a photon is absorbed by the Earth, we have a certain change in momentum. However, if it's reflected, not only do we arrest this momentum, but we also provide it with its reflected momentum, which means the change in momentum for a reflected photon will be larger, and therefore so too will be the force experienced by the Earth. When light is reflected, it imparts more momentum to the Earth, increasing the force. Question 2. The history of sailing in New Zealand goes right back to its original settlement by ancestors of Māori more than 700 years ago. The ancestors from Polynesia designed double-hulled boats with triangular sails called wakahaurua that were strong, stable, and most importantly, able to sail into the wind. This allowed them to carry out exploratory voyages. From such exploration, they were able to plan and carry out migration to Aotearoa. Wakahaurua are able to sail against the wind by heading at an angle to the wind, as shown in the simplified diagram below right. As measured by a stationary observer, the initial wind velocity is 10 meters per second from the north, the velocity of the wakahaurua is 6 meters per second to the northeast, and the final wind velocity is 10 meters per second towards the southwest, in the opposite direction to the velocity of the wakahaurua. By considering the wind direction before and after striking the sails, use impulse and momentum to explain how the wind produces a force on the sail. As we can see from our diagram, our wind experiences a change in direction, meaning that it experiences a change in momentum, meaning that a force must be applied to it. The force applied to the wind is going to be equal and opposite to the force applied to the wakahaurua. Because the wind has changed direction, it must have experienced a momentum change, and therefore a force. Via Newton's third law, there must be an equal and opposite force on the waka. Explain how the wind produces a force on the wakahaurua that has a component in the direction that the wakahaurua is travelling. Use the grid below to draw a vector diagram to help your explanation. The vectors for the initial wind velocity, the final wind velocity, and the velocity of the wakahaurua are drawn on the grid to help you. Start your answer by finding the vector for the change in the velocity of the wind. We can find the change by taking the final and subtracting the initial. So if we start our final here, that goes along 7 squares, and down 7 squares. Now subtracting our initial, which means we add on our initial vector but in the opposite direction, we see that this is 10 squares long. That means that our change in our wind velocity is this vector here. This is the direction of the change in momentum and the force applied to the wind, which means the force on our waka must be in the opposite direction. The change in wind velocity is northwest, therefore so too must be the change in momentum and the force on the wind. Since the force on the waka is equal and opposite to the force on the wind, it must be southeast, giving it a component in the northeast velocity of the waka's direction. The motion of the wakahodoa, combined with the motion of the wind, changes both the apparent speed and direction of the wind hitting the sails. On board the moving wakahodoa, the wind appears to have a higher speed and to come from a direction further towards the front of the wakahodoa. The captain measures the wind velocity as 14.9 meters per second. That hits the sail at an angle of 28.4 degrees, as shown in the diagram on the right. The sails have a combined area of 40 meters square. The density of air is 1.23 kilograms per meter cube. Calculate the mass of air that hits the sail each second. First of all, we need to find the area of the sail to the wind. If we imagine our sail pointing like this, where this is our 40 meters squared, the area we're interested in is this area here, where we have a right angle triangle. This is our 28.4 degrees, and this is the area that we're trying to find. And so we have the opposite and our hypotenuse, so we can use our SOH relationship in SOHCAHTOA. That sine of our angle is equal to our opposite, our area, divided by our hypotenuse, our 40. Multiplying both sides by 40 gives us the equation that our area is equal to 40 sine of our angle, which is 28.4. Now our mass per second is going to equal our density of our air multiplied by our area multiplied by the velocity of our wind. One way to see this is by analyzing the units. The density of our air is kilograms per meter cubed, our area is in meter square, and our velocity is in meters per second. So we can see that our m-3 will cancel out with our m2 and our m, giving us units of kilograms per second. Putting our numbers in and making the substitution for area gives me 349 kilograms per second to 3 significant figures. The sideways force of the wind on the sails causes the wakahodoa to tilt over sideways. In strong winds, the upwind side of the hiwi or hull may lift out of the water altogether. Explain how the double hull design of the wakahodoa helps it stay upright in strong winds. You may wish to add information to the diagram to illustrate your answer. As our waka tilts, we end up with this end behaving like a pivot, and with this end out of the water and no longer having a buoyancy force to counter the weight, it's going to produce a torque countering the torque produced by our wind. So let's write that down. The weight of the raised hiwi is no longer balanced by buoyancy, and thus produces a torque opposing the torque from the wind, pivoting about the hiwi still in the water. Explain how the tilting of the wakahodoa will affect the force produced by the wind hitting the sails. If we imagine our wind blowing in this direction here, we're going to have the maximum area of our sail when it is upright. When it tilts, however, we're going to have less of an area exposed to the wind. As the waka tilts, the cross-sectional area exposed to the wind decreases, decreasing the amount of wind striking the sail, and therefore the force. Due to the sideways component of the force from the wind, the velocity of the wakahodoa is in a slightly different direction to the direction that the hull is pointing. This slight difference in directions creates an asymmetrical flow of water around the sides of the hull, which produces a sideways force on the hull of the wakahodoa, as shown in the diagram on the right. Explain the effect the sideways force produced by the water flow around the hull will have on the direction of motion, and on the ability of the wakahodoa to stay upright in strong winds. The water flow force opposes the wind force on the waka, reducing its component in the direction of the waka's velocity, reducing the angle between the waka velocity and waka direction. Furthermore, the water flow force produces a torque in the same direction as the torque from the wind, causing the waka to tilt further. Question 3. A metal roller of mass m slides without friction down parallel conducting rails of negligible electrical resistance. The rails are separated by a distance L and are connected to each other at the bottom by a resistance R, forming a closed rectangular conducting loop with rails and the roller. The plane of the rails makes an angle theta with the horizontal, and a uniform vertical magnetic field B exists throughout the region. As the metal roller slides down the rails through the magnetic field, it reaches a constant velocity V. Show that the constant velocity achieved by the roller through the magnetic field is given by the relationship here. What we need to think about is the forces acting on the roller. First of all, we have a force of gravity acting downwards, and because we have a tilted rail, there's going to be a component of that in the rail direction. Now, because we have our metal rod going through a magnetic field, using the right hand rule and pointing our fingers upwards for the magnetic field, our thumb in the direction that the rod is traveling, your palm is going to be pointing in that direction there, indicating the direction of the current. Now, because we have a current flowing through this rod, if we point our thumb in that current's direction and our fingers upwards for the magnetic field, your palm is going to point in opposition to the gravitational acceleration. And so the root of finding this equation is recognizing the balance between the gravitational acceleration in the direction of the rail and the magnetic force in opposition to it. Let's first find the gravitational force in the direction of the rail. Now, if we think of our gravitational force downwards, given by the mass times the gravitational acceleration, we have the component directed down our rails, which is what we're interested in, as well as the component that isn't. This gives us a right-angled triangle, where this is the force that we're trying to find, and this is our angle. We can use the sine relationship in SOHCAHTOA, that sine of our angle is equal to the component of our force directed down the rail divided by the total gravitational force mg. Multiplying both sides by mg and swapping them around, we get mg sine theta. So that gives us our gravitational force. We now need to find the magnetic one, and that's going to require a couple of steps. First of all, we need to determine the current induced in this rod, and then we need to determine the force upon it. Now, we can determine the voltage induced across this rod using the equation voltage equals BVL, where the lowercase v is the velocity of our rod, but because our velocity is not perpendicular to our magnetic field lines, where our angle to the perpendicular is our angle theta. Now, we know we have the maximum effect when our theta is equal to 0, because at that point our velocity is perpendicular to our magnetic field. And we know we'll have 0 effect when our angle is at 90 degrees, because our velocity would then be parallel. This is one way of figuring out that we need to multiply this by cosine of our theta, because cosine of 0 is 1, and cosine of 90 is 0. In other words, cosine is at a maximum when the angle is 0, and a minimum when the angle is 90. What we also know is that V equals IR. So we can solve this for current by dividing both sides by resistance and swapping them around. And now we can find our magnetic force. The equation for the magnetic force on a current is BIL, but because we're not perpendicular, similar to our current induced, we need to once again multiply it by cosine theta. Substituting in our current equation here, we now have both of our forces, and in the case where we have a constant velocity, these forces must be equal. So our Fm is going to equal our Fg, where we can substitute those two equations. Solving this for velocity by multiplying both sides by resistance, and then dividing by b squared, l squared, and cosine squared theta. Finally, we know that tan theta is equal to sine theta over cosine theta, where we have a sine theta and a cosine theta with one cosine theta left over, meaning that we can substitute in that tan, giving us the equation that we're trying to find. Explain what difference, if any, it makes to the constant velocity v if the magnetic field is in the opposite direction. If the field is opposite, the induced current will be opposite, since the magnetic force depends on the field and current direction. If one was opposite, the force would be opposite. Because both are, the opposites negate each other. The force is therefore unchanged in both size and direction, and so too is the constant velocity. For small values of theta, equation 1 may be approximated as this thing here. An experiment is set up with b equals 2, l equals 0.5, m equals 5 times 10 to the minus 3, and r equals 10. Determine the accuracy of equation 2 compared with equation 1 at theta equals 25 degrees, or 0.436 radians. Recalling our equation 1 and putting in our equation 2, I recognize that both equations have mgr divided by b squared l squared, so I'm going to save myself a little bit of time and calculate that thing separately. Putting in those numbers gives me 0.4905 to 4 significant figures. Substituting that for equation 1 and putting our angle in gives me 0.2521 meters per second to 4 significant figures. Doing the same for equation 2 gives me 0.2477 meters per second. Finding the percentage difference between these two gives me 1.75% to 3 significant figures. By calculating the velocity at the high angle of theta equals 85, explain if this equipment would be suitable for testing whether equation 1 is accurate at high angles of theta. What we need to know is that if we have a high angle, at what velocity is our constant velocity going to be achieved, and then given the size of our equipment, we can use conservation of energy to determine the height that would be required. Finding our velocity using our equation 1, where I'm using my 4905 that I calculated earlier to make the calculation simpler. And in this case I'm using degrees and making sure my calculator reflects that. That gives me 64.3 meters per second to 3 significant figures. Let's now find the height. We can do this by assuming that our gravitational potential energy is equal to our kinetic energy, where Eg is mgh, and Ek is half mv squared. We can divide both sides by mass to cancel that out, and solve for h by dividing both sides by g. Putting our numbers in gives me 211 meters to 3 significant figures, and so the height required will exceed 211 meters, which is too large for the equipment. Explain whether equation 1 remains valid if the roller rolls rather than slides down the slope. When the roller slides, it has kinetic energy, and when it rolls, it has rotational kinetic energy. And so we have our linear kinetic energy being sapped by our rotational kinetic energy, but equation 1 does not depend on the balance of our energies, it depends on the balance between our forces. Whether or not the roller rolls or slides will have no effect on our gravitational force because it's not going to affect our mass or our gravity, and it's not going to affect our magnetic force because the field is the same, the length is the same, and the velocity required for these forces to balance is the same, therefore our induced current is the same. Equation 1 is dependent upon the relative sizes of the gravitational and magnetic forces. Neither is affected by an increase in rotational kinetic energy or a decrease in linear kinetic energy, so the equation remains valid. Question 4. The James Webb Space Telescope has a mass of 6.16 times 10 to the 3 kilograms. It was launched on Christmas Day 2021 and is now orbiting at a point called the L2 Lagrange point, where it will remain in a direct line with the Sun and the Earth as shown right. State the period of the orbit of the James Webb Space Telescope around the Sun. It orbits with the Earth, so it's going to have the same period as the Earth. Calculate the net force acting on the James Webb Space Telescope at the L2 point. The James Webb is going to experience a gravitational force from the Earth and a gravitational force from the Sun. Summing these together will give us our net force. Substituting Newton's law of gravitation, where me is the mass of the Earth, mj is the mass of the James Webb, ms is the mass of the Sun, re is our distance here, and rs is our distance here plus our distance here. Simplifying this by factorizing gmj out, and putting our numbers in. Giving me 36.7 newtons to 3 significant figures. An approximation for two bodies in orbit around each other is that the period t of the orbit can be determined using the relationship this here, where r is the distance between the center of masses of the two objects, and m1 is the mass of the more massive body. One assumption of the relationship above is that m1 is much greater than m2. Explain why it is necessary to assume that m1 is much greater than m2 to derive this relationship. The assumption is that m1 is stationary, and its center of mass is the center of mass of the system. This allows us to only consider the effect of m1 on m2 without considering the effect of m2 on m1, which would make the mathematics uglier. State another key assumption of this relationship. That is that the only forces acting are gravitational. In the case that m1 is not much larger than m2, show that the period of the orbit is given by the relationship this here. Any other assumptions made for the relationship given on page 12 are still valid. In this situation, we can model the system as m1 and m2 orbiting their shared centre of mass. Whereas in our previous question r is the distance between the masses, and we'll define the distance from the centre of mass to m2 as the letter x. We know that the centripetal force experienced by m2 is equal to the gravitational force, where the centripetal force on m2 is n2v2 divided by x because that is the radius of its circle, recalling that we're modelling it going around the centre of mass, not m1. The gravitational force is just given by Newton's law as usual. Now before we go further, we can find our x using this formula on your formula sheet, where because we're defining this as our x equals 0, our distance to m1 is going to equal r, and our distance to x2 is 0. Let's now find v. We know that velocity is distance divided by time, where the distance is our circumference, 2 pi x. Remember that we're using x because x is the radius of our motion, not r. And our time is just our period. And we can write our v squared as 4 pi squared x squared divided by t squared, making that substitution. We can divide out our m2 and also our x from our power, solving for t squared by flipping both sides, and now multiplying both sides by 4 pi squared x, substituting in for our x, dividing out our m1, gives us our final equation. The phases of the moon are caused by the relative positions of the sun, earth and moon. A full moon occurs when the sun, earth and moon are directly aligned. The moon takes 27.3 days to complete one 360-degree orbit around the earth. However, because the moon must orbit more than 360 degrees to return to a direct alignment with the sun and earth, as shown in the diagram on the right, the time between one full moon and the next is more than 27.3 days. Show that the time between one full moon and the next is 29.5 days. The first thing we can recognize is that this angle that Earth traces is the same angle that the moon needs to additionally go. And so the total angle that our moon needs to go is going to be one full cycle plus our additional angle. Recalling that theta is equal to omega t, our total angle that the moon traces is going to equal the angular velocity of the moon multiplied by its total period that we're trying to find. We can similarly replace our theta, knowing that this additional angle is the angle that the Earth traces in that same period t, meaning we can replace it with the angular velocity of the Earth multiplied by the same period. Solving this for period by subtracting omega et from both sides, factorizing period out, and now dividing both sides by our brackets. Problem is, we don't know omega m or omega e, but what we do know, similar to this equation here, is that our angular velocity is going to be the angle for a full rotation divided by the time for a full rotation, meaning we can substitute omega e for 2 pi over te and omega m for 2 pi over tm, where our te, the period of the Earth, is 365.25 days, which we found in the first question, and tm is at 27.3. Making that substitution, dividing our 2 pi out, and now putting in our numbers. Gives me 29.5 days to 3 significant figures, which is what we're trying to find. And we're done.